Right. So last class we discussed how electromagnetic waves are generated, what their properties are, how to calculate the speed, how to write the equation and all. We are currently discussing about sinusoidal electromagnetic waves, where the electric field oscillates as a sine function. Okay, sine, cosine, as I said, they are the same. You can convert one from the other, one to the other and so on. Can one of you tell me the equation for electric field in an electromagnetic wave? General equation. Suppose the wave is propagating in the positive x direction. How do you write the equation for the electric field of that electromagnetic wave?
E naught sine omega t minus kx.
E naught sine. Yeah, whether you take omega t minus kx or kx minus omega t, it's fine. It's just a matter of phase. Okay. You ensure that the coefficients are of opposite sign, then it is traveling in the positive x direction plus some phase constant. Fine. Let's say this is the electric field in the y direction, so you can put a j cap here. And electromagnetic wave, it will have a magnetic field also. Let's assume magnetic field is in the z direction. You can write its equation like this. We know that the electric field and magnetic field will be in the same phase. Only their peak values will be different. And can one of you quickly tell me how E naught is related to B naught? Suppose the wave is traveling in vacuum. How are E naught and B naught related? Electric field amplitude and magnet.
Electric field by magnetic field is C.
C. Okay. So you can write E naught is equal to C times of B naught. The ratio is the speed of the wave. Fine. Now we know waves carry energy and momentum. So electromagnetic wave also should be carrying some energy and momentum. It carries energy in its electric field and magnetic field. Okay. So we will use the ideas that we had derived earlier. We know that if there's an electric field present in space, in a certain region of space, there is energy stored in that space. Okay. And we know the expression for energy per unit volume, that is energy density in an electric field. We will use that to write an expression for energy density in an electromagnetic wave. Because we have the field expression here. We know how much electric field it produces. Then we will be able to write what is the energy density in that wave due to the electric field. And we also know the expression for energy density in a magnetic field. We know how much magnetic field it produces. So we'll be able to write an expression for energy density in the magnetic field as well. Combine both energy due to electric field and energy due to magnetic field, you'll get the energy in the electromagnetic wave. Okay. So first, energy density in the electric field of an EM wave. Generally, if there's an electric field E in vacuum, how much is the energy density, or what's the formula for energy density in the electric field? We had derived this long back when we discussed parallel plate capacitor. If the electric field is E, then how much is the energy density in that electric field? Okay, it is half epsilon naught E square. Fine, assuming the medium is vacuum. Fine. Now, the electric field created by an electromagnetic wave is of this kind, E naught sine omega t or kx plus or minus omega t plus phi. Okay. It's non-constant, non-uniform. Okay. At a given time, from point to point, it will be different. At a given point, from time to time, it will keep changing. Okay. Now, if the electric field keeps changing, then the energy density, that is the energy per unit volume in that field, will also keep changing, because energy per unit volume is half epsilon naught E square. Then if it's the electric field created by an EM wave, then E square would be E naught square sine square of all that, omega t plus minus kx plus phi. So simply because the electric field produced by an EM wave is non-constant, is variable, the energy density stored in the electric field, or energy density of the electric field, also keeps changing from time to time. Point to point also it will keep changing. Okay. So this is the general expression for energy density in the electric field of an EM wave. At any time, at any point, you just substitute the corresponding x coordinate and time. You can tell what is the energy density. Okay. Let's consider one point now. At a particular point, let's say x naught. Okay. The energy per unit density, the energy per unit volume, that's the energy density, becomes half epsilon naught E naught square sine square omega t. T is a variable. Okay. Time keeps on changing. Plus or minus k, we are fixing the x coordinate, and the phase constant is a constant anyway. So this entire part becomes constant. Okay. So it's effectively like half epsilon naught E naught square sine square of omega t plus some unknown constant. Not exactly unknown. If you substitute the x coordinate, you know that constant also. Okay. Now from time to time, this value will keep changing. So we'll be interested in finding out the average energy density in the, or yeah, average energy density in the in the electromagnetic wave. One of you tell me, what is the average value of the sine square function?
Half, sir.
Half. Okay, that half gets multiplied with this. Therefore, the average energy density stored in the electric field of an EM wave becomes 1 by 4 epsilon naught E naught square. There is another way also to write it. We can also write it as half epsilon naught E naught by root 2 whole square. Can one of you quickly tell me what E naught by root 2 is? E naught is the peak value of the electric field. What is E naught by root 2?
The RMS value.
RMS value. Okay. Or you can say the effective electric field. So you can write it as half epsilon naught E RMS squared. Because we know that the electric field of an EM wave is variable. So whenever any function is variable, if you want the energy, you take the effective value of that function. Okay. So E RMS squared. Fine. So this is the average energy density in the electric field of an EM wave. Only the electric field. This much. Similarly, we can derive an expression for energy density in the magnetic field of an EM wave. The magnetic field in an electromagnetic wave is represented like this: B naught sine, again, omega t plus or minus kx plus phi. B naught being the peak value or the amplitude of magnetic field. The rest is a variable term. Now, if magnetic field keeps changing from point to point, time to time, then the energy density in the magnetic field also will be varying from time to time and from point to point. So here also we'll be interested in the average value of the energy density. Okay. Can one of you tell me the formula for energy density in a magnetic field? General formula. In a magnetic field B, how much is the energy per unit volume? Okay, see the formula is similar to what we have for electric field. In electric field, it is half epsilon naught E square, no? For magnetic field, half will be as it is. Wherever you have epsilon naught in electrostatics, when it comes to magnetism, you'll have 1 by mu naught. And instead of electric field, you take magnetic field, that's all. Okay, so it is B square by 2 mu naught. Therefore, in an electromagnetic wave, the energy per unit volume in the magnetic field becomes, now magnetic field has an equation here, it will become B naught square sine square omega t plus or minus kx plus phi, and divide that by 2 mu naught. That's the energy density in the magnetic field of an EM wave at any point at any time. Now again, same analysis. If you fix the point at a particular point, then this whole thing becomes constant. Then at a particular point or position, you can call it anything, the energy per unit volume in the magnetic field becomes B naught square sine square omega t plus some constant divided by 2 mu naught. Keeps changing from time to time, obviously, because at a particular point, the magnetic field strength keeps changing from time to time. Therefore, the average energy per unit volume, that's the average energy density in the magnetic field of an EM wave, then becomes, again, sine square function average is half. So it becomes 1 by 4 B naught square by mu naught, which can also be written as B RMS square divided by 2 mu naught. Okay, this is the average energy density in the magnetic field of an EM wave. Okay, so at a particular point, when an EM wave is passing through that point, we have derived expressions for average energy density in its electric field and the average energy density in its magnetic field. Now you combine both, you get the total average energy density in the electromagnetic wave. Okay, therefore, average energy density in the EM wave becomes the average energy density in its electric field plus the average energy density in its magnetic field. Now, why I am stressing so much on this derivation is, like in mains and all, they may ask you direct questions. You can remember the direct formula. But in some exams where they want to test your concept, they may change the equation a little bit. Now, for the sine function, you know, sine square average is half. Instead of sine function, they may give you some other function and ask you what is the average energy density in an EM wave. Okay, they may frame a new equation of an EM wave and ask you what is the energy density in it. You should know how to derive. Okay, so we are doing it just from the basics. We know it consists an electric field and a magnetic field. We are writing energy density in the electric field, energy density in magnetic field, averaging it because the electric field and magnetic field are variable. Okay, and then combine both of them, that becomes the total energy density at a particular, or we should not say point, total energy density in the electromagnetic wave. Okay, so combine these two expressions. Due to electric field, it was 1 by 4 epsilon naught E naught square. And due to magnetic field, it was 1 by 4 B naught square by mu naught. So some energy contributed by electric field, some energy not contributed, I should say, some energy stored in electric field, some energy stored in its magnetic field. Okay. Now, E naught and B naught are related to each other. The relation between them being E naught is equal to C times of B naught. C is the speed of electromagnetic wave in vacuum. We are assuming the medium as vacuum. Okay. So this becomes 1 by under root mu naught epsilon naught into B naught. Now square both sides. If you square, you get E naught square is equal to B naught square divided by mu naught epsilon naught. Send epsilon naught that side. This means epsilon naught E naught square is equal to B naught square divided by mu naught. This is interesting. Epsilon naught E naught square you find here. B naught square by mu naught you find here. Both of them have the same coefficient 1 by 4, 1 by 4. It means, okay, from this equation, you can say that these two are equal. Okay, this is what is interesting. The average energy density in the electric field of an EM wave is same as the average energy density in its magnetic field. Okay, although the magnitudes of E naught, B naught, numerically they are very different. Okay, there's a large difference. There's a huge ratio between them numerically. Okay, but as quantities, they are not even supposed to be compared. You can't compare an electric field and a magnetic field. They are completely different quantities. And if you look at the energy carried by the electric field of an EM wave and the magnetic field of an EM wave, it happens to be equal. Okay. Therefore, energy density average in the magnetic field of an EM wave is equal to energy density average in the electric field of the EM wave. Okay, this is very important. And if these two terms are equal, you can add them up and write it as 2 times of the first term or 2 times of the second term. It's like you have some x is equal to a plus b, and if a and b are equal, you can write it as 2a. You can also write it as 2b. Okay, so same thing can be done with energy density. Therefore, energy per unit volume total can be written as 2 times of the first term. If you write, it will be half epsilon naught E naught square. You can also write it as half B naught square by mu naught. So the energy density in an EM wave can be expressed completely in terms of its electric field or completely in terms of its magnetic field also. We don't mean that all the energy is in the electric field only or all the energy is in the magnetic field only. Both of them carry equal amounts of energy. You can write it entirely in terms of one of them. Okay, that's the idea. Is the derivation clear to all of you? How we derived the average energy density in an electromagnetic wave? Okay, we are using the formula for energy density in electric field generally and energy density in magnetic field generally. And we are applying that to electric field of an EM wave, magnetic field of an EM wave. And the interesting thing is that we find that the electric field and magnetic field carry equal amount of energy. Okay. So if you know what we have derived here finally is the energy per unit volume. Okay. So if you know how much volume is filled by how much volume is filled by the electromagnetic waves, okay, then you can tell what is the total energy in that volume. This is just the expression for energy per unit volume. Multiply it with volume, you'll get the total energy. Okay. Next, intensity of electromagnetic waves. This is very, very important. Can any of you define intensity? General definition of intensity. Basic definition of intensity, or what you understand from it. Okay, just a moment. I'll show you an example. Okay. You all must have done this, or you know that you all must be knowing that this happens when you hold a magnifying glass, okay, under sunlight. The magnifying glass, what does it do? Whatever sunlight falls on the glass, okay, like on this surface, the light that is falling, it focuses it onto a particular point. We'll discuss this in detail in the next chapter, actually, optics. Magnifying glass is a convex lens. It's a converging lens. Okay. The light coming from the sun is a parallel beam of light. That parallel beam of light converges to a single point. Okay. We say it gets focused. Now observe this picture very carefully. Let me mark 3 points here. 1 point A and this point B. I hope you all are able to see. And the third point is C. Okay. Now A is under direct sunlight. Okay, you can see there is light falling on that surface. A is under direct sunlight. So had sunlight fallen on that surface, normally the brightness would be as much as you see at the point A. So A is like normal sunlight. Okay, the brightness at A like is the normal brightness that you get. At B, the brightness is less. Okay, actually at B, there is no direct sunlight falling. Okay, you can see a shadow there. But you can still see the surface also. It's not completely dark. You can see the surface at B. There's no sunlight falling on it, but other light is falling on it. Maybe some light from some other source or light reflected from something else is falling at B. Direct light from the sun is not falling at B. Okay, so at B there is no direct sunlight. Then at C, there is sunlight and it is focused. All the light that was falling on this magnifying glass, okay, all the light that was falling on this much area, the area of that, the circular area of that glass, gets focused to a single point or maybe a small area. Fine. So at C, you have focused sunlight. Okay. Now, if you have ever tried this, if you put a sheet of paper, no, then at the point C, the sheet of paper starts burning also in some time. Now you all tell me this. If you put a sheet of paper in direct sunlight, no magnifying glass, you put the sheet of paper in direct sunlight, will it burn? If a sheet of paper is left in direct sunlight, maybe afternoon sunlight itself, will it burn?
No, sir.
It won't. Okay. Like howsoever long you leave it in the sunlight, you won't see it burning. That does not happen. But the same sheet of paper, if you use a magnifying glass and focus sunlight onto one point, at that point the sheet of paper starts burning. Why? Not just sheet of paper, wood will burn, cloth will burn. Okay. Why do you think that happens?
That it's because the sunlight is like concentrated on that certain point, and it's very intense.
Intense. Okay. Okay. So basically, this is what intensity is. How the energy is spread over a surface. Fine. And of course, there is a time factor also. So intensity, by definition, is energy incident. You can take energy incident or energy passing, anything of that sort, per unit area per unit time. Okay. So intensity basically depends on how much energy is being delivered per unit time and in how much area it is being delivered. Okay, so energy per unit area per unit time is what we call as intensity generally. And yeah, here the difference between the light at A and the light at C is intensity itself. The light that is incident on this much area is getting focused on a very small area at C. Okay, so the energy incident per unit area is decreasing. Is increasing. Area is decreasing, so energy per area is increasing. Okay, and it is incident at a particular rate also. Time factor also needs to be considered. But basically, this is what is intensity, how focused the energy is per unit time. Fine. Now we know electromagnetic waves carry energy. We just derived an expression for energy density in the electromagnetic wave. Now when electromagnetic waves are incident over a surface, okay, over a certain area, we should find out what is the intensity on that surface. Means how much energy is incident per unit time per unit area is what we need to find out. Okay. Assume electromagnetic waves are traveling to the right. Okay, let's say there is a bundle of electromagnetic waves traveling to the right, parallel to each other. Assume they are incident on a surface. Surface could be of any shape. I'll assume a rectangular surface like this. So we are looking at it from an angle. Actually, there should be waves spread all over this surface. Just a moment. Okay, and assume they are crossing over to the other side. Fine. So as the EM waves pass through this surface, energy will be passing through this surface. Or suppose it is blocking those waves, energy is at least falling on that surface. Okay. Assume the waves are traveling with a speed v. Now we know energy per unit volume, energy density in the electromagnetic wave is half epsilon naught E naught square. Or you can also write it as half B naught square by mu naught. Any one expression can be used. We know the energy per unit volume. Fine. So let's say EM waves are passing through the surface like this. Now what we need is intensity, energy per unit time per unit area. Okay, let's say the area of the surface is A, capital A, that rectangular surface. Let's consider a time dt, a short time interval dt. And now in a short time interval dt, what will happen? The waves will travel forward by some distance. Okay. Distance traveled by the waves or distance moved by the waves will be a small distance dx, or ds also you can write it, not a big deal, which is speed multiplied with time. So the waves will move forward by that much distance. Now if the waves move forward by that much distance, whatever energy is trapped in that distance gets incident on this surface. Okay, what I'm saying, you can visualize it like this also. Let's say this is an EM wave. Assume there is a surface here or a boundary here. Now the EM wave carries energy. Fine. We don't know the total energy in the wave. It depends on how long the wave is, how much space it is occupying and all. But when this wave moves forward, then maybe it moves forward by this much distance. If the wave moves forward by some distance, the energy in that part of the wave passes through this boundary. That's the idea we are using. So in a small time dt, the waves move forward by a distance v dt. Okay. So when they move forward, maybe they will reach somewhere here. Okay, I'll have to send this back. Just a moment. Okay, it's somewhat like this. All the energy trapped in this space, okay, between these two imaginary surfaces, all that energy passes through the first surface in a time dt. So you can call that volume as d capital V. Are you able to visualize this? Rishi is the, are you able to visualize the picture?
Yes, sir.
Isha, is it clear?
Yes, sir.
Electromagnetic waves are traveling forward. So in a short time dt, if you consider the distance by which they move forward, the distance also can be shown here. This is the distance that we are talking about. And they are passing through an area. So area into distance becomes that volume dV. You can write it as A into ds. All the energy in that volume must have passed through the first surface in this time dt. So this is the idea we use to derive intensity. Okay. See, this idea is very important because they can ask you in the exam, they can ask you to derive intensity in different cases. Here we have taken a parallel beam of light, parallel beam of electromagnetic waves. Then it's easy to imagine a volume like this. Okay, randomly I took a surface of area A, some thickness, some distance ds, A into ds becomes the volume. They may give you some other kinds of electromagnetic wave distribution also. Okay, so you need to imagine a surface perpendicular to that wave distribution because waves will be passing through that surface. So you have to imagine the surface through which the waves are passing and then consider a small distance. Then you will get a volume through which the energy has passed. Okay, volume which consists that energy. Anyway, here the volume is A into ds. Okay, therefore energy that passes through the area A in time dt, what will it be? We know energy per unit volume. Multiplied with volume, you'll get the energy. Energy per unit volume is half epsilon naught E naught square. Okay. Electric field energy plus magnetic field energy combined is this much per unit volume. Multiply that with the volume. The volume here is nothing but A into ds. ds is nothing but v dt, speed multiplied with the time. Therefore, that is the energy that passes through the surface of area A in a short time dt. So we know how much energy is passing in a certain amount of time. Now we can write the expression for intensity. Intensity is energy per unit time per unit area. So you have to divide this by A and T, or A and dt I should say. Then it becomes half epsilon naught E naught square. A and dt get divided, they get cancelled. You will be left with V. That's all. Therefore, intensity of an EM wave is half epsilon naught E naught square multiplied with V, where V is the speed with which they are traveling. You can also write it as half B naught square by mu naught into V. You can even remember it like this. Intensity is energy density multiplied with the speed. That's all. Because half epsilon naught E naught square is nothing but energy density. Okay, average energy density. V is the speed. In vacuum, the expression changes to half epsilon naught E naught square into C, because C is the speed of electromagnetic waves in vacuum. Okay, so let's go through the derivation once again. We visualized electromagnetic waves. The arrows here represent the direction of propagation of the waves. Okay, so you can imagine there is an EM wave going like this, or there are many EM waves going like this. So the EM waves are passing through a cross-sectional area of A. So when waves pass through a cross-sectional area A, it's like energy is passing through that area. So what we did was we considered a small interval dt. In that time dt, we know what distance the waves are going to travel. If waves travel that much distance, then energy also travels that much distance, because waves carry energy with them. Then that distance multiplied with area will give us a small volume. All the energy trapped in that volume must have passed through this surface. So we know energy density, that is energy per unit volume. Multiply that with volume, you will get to know how much energy has passed through the surface in this time dt. Then you can find out energy per unit area per unit time. That's what we have done. Okay, practice these derivations once later. Right. Let's solve some problems based on this. First, suppose there is a source of EM waves, point source. You can consider it like this. Let's say S is the source of the waves. Now, can one of you tell me in which direction, or how does a point source emit waves in different directions? Or if you draw waves or draw the path followed by waves emerging from a point source, what will the paths look like? Or what will the pattern look like? Okay, consider a bulb. You switch on the bulb. In which direction does the bulb send light or bulb emit light? Rishi, can you answer? If the bulb in a room is switched on, in which direction does the light travel?
Or in all directions.
In all directions, correct. Suppose the bulb has a holder. Okay, you imagine it somewhat like this. Let's say this is the bulb holder. And the bulb is connected here. You know, it sends light in all directions, it emits light in all directions. But does it emit light this way?
No, sir.
It cannot, because it is blocked, okay, by the holder or whatever it is. Okay, it is blocked. Now, basically, a point source doesn't have any connections like this. Fine. In real life, point source of light is difficult to create, but they they don't even exist actually. But a star, when you see from very far away, it looks like a point source of light, point source of EM waves. So it's like that. Now, this bulb has a certain preference. On one side, the light is blocked, so it can only send light the other way. Okay. But the point source does not have anything to block the light that it is producing or the EM waves that it is producing. So what happens is the radiation produced by a point source travels uniformly in all directions or is distributed uniformly in all directions. Why should there be a preferred direction for a point? Okay, it will not be there. So the radiation will be distributed uniformly in all directions. So whatever energy it emits, it spreads out uniformly in all directions. This is somewhat like the electric field pattern of a point charge. Fine. And you have to remember this analogy actually. If you want to visualize how a certain source emits waves, okay? How means in which direction it emits waves. If you want to visualize, you visualize the electric field produced by a similar distribution of charge. You know the field, electric field of a point charge, no? Radially outward field lines will be there. So if a point source emits waves, they'll also be spread radially outward like this. Okay. Fine, let these be. So assume there is a point source of electromagnetic waves emitting a power P. Can one of you quickly tell me the definition of power? Basically, what does power mean?
So it's like the amount of energy.
Power is not energy. we could have called it energy only, no? Isha, what is power? Okay. Tell me.
Sir, it's like the rate at which the work is done.
Yeah, rate at which work is done or rate at which energy is produced, energy is consumed. That is what is power. Okay. How much energy per unit time or how much work per unit time is what we call as power. So let's say this point source emits a power P. Means P joules of energy is emitted per second. Okay, so how much energy is emitted per second is known to us. Fine. One of you tell me from your everyday experience. Suppose there is a bulb, small bulb, or a small speaker. Okay. Bulb emits light waves, speaker emits sound waves. Both are emitting waves. Okay. As you go away from the bulb or away from the speaker, what happens to the intensity that you observe? For example, if it's a bulb, as you go away from the bulb, what happens to the brightness? If it's a speaker, as you go away from the speaker, what happens to its loudness?
The more you move away, the lesser you hear from the speaker.
Greater the distance, lesser the sound or light. Okay. It's actually not lesser the sound or light. We should say lesser the sound or light per unit area per unit time. Now see, whether you feel an object as bright or dim depends on how much light enters into your eye. Your eye has a fixed area. The lens of your eye has a fixed area of cross section. Light has to enter into that cross section. Okay. So what happens here? Assume this is a source of light. Okay, a round source. You can think of it as a point source also, not an issue. Okay. Now it emits waves. It emits waves in every direction. Okay. One wave goes like this. Just a moment. One wave like this. In every possible direction, you will have waves. Just give me a few seconds. This is useful for optics also actually. Let's consider a few waves emitted by this source of light. Now, if you are very close to that source, okay, assume this is the eye of the observer. Okay, the eye lens. If the observer is very close to the source, you will see more waves or more waves entering into the observer's eye. In case of sound, it's the number of sound waves entering into your ear, the opening of your ear. Okay. As the observer moves away from the source of light, you can see that the number of waves entering into the observer's eye decreases. Okay, at some points it is 3, at some points it is 2, at some points it is 1. Fine. Now, the wave speed is same everywhere. Fine. So energy is traveling at a particular speed. At whatever speed the waves are traveling, at the same speed the energy is traveling. But how much energy enters into that area, how much energy is incident per unit area keeps changing as you go away from the source. Okay. And see, this does not happen with every source. Point source is a source which emits waves which are radially outward, which are diverging. The waves are going away from each other, right? In such a scenario, as you move away from the source, the intensity will decrease. Energy incident per unit area will keep on decreasing. Suppose there is a parallel beam of waves like this. Okay. Here, if you consider an observer's eye, okay, maybe somewhat like this. If a parallel beam of waves like this enter into the observer's eye, for that observer or for that pattern of waves, the intensity will be same everywhere, even if you move backward or forward. Okay. So what happens to the brightness, what happens to the energy falling per unit area depends on how the waves are propagating. Okay. That is why it is important to visualize the pattern of waves produced by a particular source. Okay, we'll solve some more questions, you'll understand. But see, if it's a point source, it emits waves radially outward, so the waves are diverging. So as you go away from the point source, intensity will decrease because the energy incident per unit area is going to decrease. Right. Now the question is, this point source is emitting a power P, means you know how much energy is emitted per unit time. That energy spreads out in all directions. You have to find out the intensity at a certain point P. Okay, P we have called as power. Let's call the point as A. You have to find out how much is the intensity at that point. Now observe what we know. We know the power emitted by the source. That is, energy per unit time is known by us. Energy emitted per unit time. And you are asked to calculate intensity at a certain distance. Can one of you quickly tell me the basic formula for intensity? Not in case of EM waves. General formula for intensity is what? Like by definition.
Sir, is it power by
By?
4 pi r?
See, Rishi, you are going into a specific case. I asked you generally by definition, what is the formula for intensity? Isha, can you tell?
Power by area, sir.
Power by area. Okay. Energy per unit time per unit area. That is the basic definition of intensity. If it is light energy, then it becomes intensity of light. If it is sound energy, it becomes intensity of sound. If it is heat energy, it becomes intensity of heat. Okay. So energy per unit time per unit area is intensity. Now you are asked to derive an expression for intensity at a certain distance from the source. Let the distance be x. How will you proceed? Expression for intensity at a certain distance from the source. How will you proceed? We need to know how much energy is incident per unit area per unit time. But you are asked intensity at a point, not an area. What will you do? Okay, listen. The question is asking you to calculate intensity at a point, but by definition, intensity is defined for an area. Then what do they mean by intensity at a point? Let us discuss that. Suppose there's a surface. Okay. Assume radiation is falling on, light is falling, or sound is passing through it, or heat is being incident on it, whatever it is. Let's say the intensity over this area is I, and assume it has uniform intensity. Okay, means intensity all over that area is the same. The brightness everywhere is the same, or the loudness everywhere on that area is same. In that case, intensity of the area, intensity over the area will be same as the intensity at any point on that area. Okay, so the idea is this. If a surface has uniform intensity I, then the intensity at any one point of that surface is also I itself. Okay, now at a certain distance from a point source, I'll redraw the diagram here. At a certain distance from a point source, you are asked to calculate the intensity at a particular point. Fine. S is a point source. Now tell me, can you all think of an area of which this point is a part? Okay, the point where you want the intensity should be part of that area, and the intensity on that area should be uniform. Can you visualize such an area in this case?
Can you repeat your question?
Yeah. Can you visualize a surface? I'll write it here. Over which the intensity will be uniform, and that point, okay, we call that point as A, and that point A lies on that surface. How will such a surface look? Okay, think of it this way. Assume there is a bulb, small bulb. You know that when you move away from the bulb, its brightness will become lesser and lesser. No, I'm not saying the bulb's brightness as such, but the brightness observed by you will decrease. Okay. So tell me now, suppose this is a bulb. Can you think of multiple positions or points around this bulb from where the brightness will appear the same? Can you find out multiple points around this bulb or near this bulb from where, if you look at the bulb, the brightness will be the same?
Yes, sir.
Okay. How should those points be arranged? Or how will those points be
The,
arranged?
like, let's say it should be equidistant from like the,
Good, good. It should be equidistant. Okay.
and it should like surround it in like a circular path kind of.
Correct, correct. So if you take points which are at the same distance from this source, okay, same distance x here, same distance x this way. If you take points which are equidistant from the source, they will all experience the same intensity, because we know intensity changes based on distance. Okay, so you fix the distance, then you'll be fixing the intensity. Now in the plane of the screen, this looks like a circle, as Rishi is saying, but we have to think in 3 dimensions. The surface becomes a spherical surface. Okay, so if you consider a sphere around this point source, okay, sphere of what radius? Sphere of radius x itself, where x is the distance where you're asked to find out the intensity. And the center of the sphere should be on the point source. If you consider a sphere like this, then the brightness of the bulb when you see from any point on that sphere will be the same. Isha, are you convinced with this or not?
Yes, sir.
So it all depends on how the waves are traveling. It's a point source, no? The waves diverge uniformly from the source. Okay, there's no preferred direction for the waves. They'll all get distributed. They'll get distributed uniformly in all directions. Okay, this is taking time. Let me just draw it off like this with hand. So if you fix a particular distance from the source, the intensity at that distance is going to be uniform. So see, what was the question? The question was to calculate intensity at a distance x from the source. Intensity at a point which is at a distance x from the source. Now, by definition, intensity is for a surface. So what we are doing is we are identifying a surface which consists that point and which also has same intensity everywhere. Now what we will do is we'll find intensity on this surface. And whatever is the intensity on this surface, same will be the intensity at that point A which you are given. That's the idea. Okay. Now, what is the shape of this surface? It's a spherical surface. I'll have to mention that it looks like a sphere. Sorry, it looks like a circle, but it's actually a sphere of radius x. Rishi, what is the surface area of a sphere?
So
Rishi or
4 pi
Rishi?
r square.
4 pi r square. So in this case, it becomes 4 pi x square. Now the source is radiating energy, or the source is radiating a power P. Means P joules of energy is emitted per second. If P joules of energy is emitted per second and energy travels with a constant speed, then the same P joules of energy per second will be crossing this sphere. Okay. Therefore, energy per unit time is P. That's the energy crossing this sphere per unit time. and the sphere has a surface area 4 pi r square, means this power is distributed over this much area. Therefore, intensity on that sphere becomes the power P divided by the area through which that power is passing. Okay, that energy is passing, cross-sectional area. So intensity will be P divided by 4 pi x square. That's the intensity over that sphere. And that sphere has uniform intensity, we know, because the points are equidistant from the source. If the sphere has the same intensity everywhere, then at a particular point of the sphere also, intensity will be this itself, P divided by 4 pi x square. Okay. So you were given a source and you were asked intensity at a certain distance from it. We first use the definition of intensity. Intensity is energy per unit time per unit area. Now we know energy per unit time already. That is given to you in the problem. Source is emitting P joules of energy per unit time. Now if it is emitting P joules of energy per unit time, then energy flows with constant velocity. Electromagnetic wave, they travel with constant velocity. Then at any point, the energy, not point actually, if you take a closed surface, okay, around this source, you take a surface of any shape, doesn't matter. Energy passing through that surface will be P itself per unit time. Because energy won't stop anywhere. No, it keeps traveling with constant speed. So you take any point in space, inflow of energy should be equal to outflow of energy, because energy is not getting trapped anywhere. So whatever energy the source is emitting per unit time, the same energy will pass through the boundary per unit time. Okay. So we know the energy per unit time on this sphere. We divided by area of the sphere. So we got energy per unit time per unit area, intensity on that sphere. Okay. Now consider another problem like this. Suppose there is an infinitely long source of light. Okay, an infinitely long linear source of light like this. Okay. Now, if it is infinitely long, the total energy emitted by it per unit time will be infinite. But what we can write now for such a source is energy emitted per unit time per unit length. Let's say it is some, okay, let's call it U itself. Energy per unit time per unit length is U. See, the total length of this source is infinite, no? So the total energy per unit time will be infinite, but per unit length, there will be a fixed amount of energy being emitted per unit time. Okay. And I'm asking you to calculate the intensity at a distance x from it. How will you do this? We know the energy emitted per unit time. We have to find out intensity. Okay, first things first. Intensity is generally defined for a surface, not for a single point. But you are asked intensity at a single point. Then you should imagine a surface of which this point is a part. Okay, you should imagine a surface which consists this point, and that surface should have uniform intensity. So first of all, can you visualize a set of points which will have the same intensity? Set of points near this source or around this source which will experience the same intensity. Okay, Rishi, you tell me. Let's call this point as A. A is at a distance x from this infinitely long source. At A, some intensity will be observed. Can you think of any other point which will have the same intensity as A?
Sir, x distance from like to the left.
At the same distance on another side, or maybe this side itself. You can take the same distance
Yeah,
x.
diagonally or anything like that.
No, diagonally should not go. Perpendicular distance only should be taken.
Sir, why not diagonally?
If you go x distance diagonally, then the point will be nearer to the source. And if point is nearer, it is likely that the intensity is high. Don't you think so?
Oh yeah, so because it's infinitely long.
Yeah. This is not a point source. Yeah, it's a linear source. So if you want to identify a surface over which the intensity will be uniform, you will have to think of points which are equidistant from the source. Now this source is a line. A set of points equidistant from a line will be cylindrical. Okay. See, by now you must have gotten some idea in your mind, some thought actually. I asked you to visualize waves like electric field lines. Now, if you are visualizing waves, if you visualize waves like electric field lines, then this surface over which the intensity will be uniform will be like the Gaussian surface for the charge distribution. Okay, if you remember, we derived electric field produced by a long linear charge by constructing a Gaussian surface like this. In fact, electric field produced by a point charge can be derived by taking a Gaussian spherical Gaussian surface like this. Okay, so I'm giving an idea. If you want to imagine a surface over which the intensity will be uniform, think of the source as a charge and think of the surface as the Gaussian surface, symmetric Gaussian surface, which we used to derive the electric fields. Okay, so for a long linear charge distribution like this, the Gaussian surface we used is a coaxial cylinder. So if you imagine a cylindrical surface around this source, at every point on that cylindrical surface, the intensity should be the same because every point of that cylindrical surface is equidistant from this source. In fact, if you visualize the waves produced by this source, the waves will be going radially outward. I should say, yeah, the waves will be traveling perpendicular to the source like this. Okay, on the upper surface, if you see, you can even visualize them like this. Okay, that will be happening at every point actually. So if you consider a coaxial cylinder, that coaxial cylinder will have points at which the intensity is same. Okay. Let's say the length of this cylinder is L. Now you can clearly see that that's cylindrical surface that we have visualized is enclosing some part of the source. The source is infinitely long, but some part of the source is enclosed in this cylindrical surface. That source length also will be L itself. Cylinder length is L. Then the length of the source trapped inside it will also be L. Whatever energy is emitted by this length of the source, that energy passes through this cylindrical surface. Okay. Now energy emitted per unit time per unit length is U. Therefore, energy per unit time per unit length is U. Therefore, energy per unit time would be U into L. Okay. That is the energy emitted per unit time by the source which is trapped inside the cylinder, by the part of the source which is trapped inside. Now, if it is emitting that much energy per unit time, that same amount of energy per unit time will pass through the cylinder. Okay, like just to make visualization better, you can imagine it like this. The energy passing through the cylinder. Okay, so we know energy per unit time. And now tell me, what is the formula for curved surface area of a cylinder? Anyone? Curved surface area of a cylinder.
There's 2 pi RH plus 2 pi R square.
That is the total area of a cylinder, total surface area. I'm asking only the curved surface area.
Oh, curved.
It will be 2 pi r multiplied with the height. Here the radius of the cylinder is x, height is L. So 2 pi x into L will be the curved area. That's the area through which the waves are passing, no? That's the area on which we want the intensity. Therefore, now the intensity becomes, intensity by definition is energy per unit time per unit area. Energy per unit time is U into L divided by the area here is 2 pi x into L. L gets cancelled. You get intensity as U divided by 2 pi x. Okay. So if it's a long linear source like this, the intensity is inversely proportional to distance from the source. If it's a point source like the one we discussed in the first problem, the intensity will be proportional to, inversely proportional to square of the distance. Okay. So for different types of sources, you will have different types of variation of intensity with the distance. Okay, I'll send you the notes. Just go through these problems, these two problems. So what all have we discussed today? First, we derived an expression for energy density in an EM wave. Okay. After that, we talked about intensity and we derived an expression for intensity of an EM wave. Okay, half epsilon naught E naught square multiplied with the speed with which it is traveling. So energy density into speed becomes intensity. Then see, if you know electric field, that is how you calculate intensity. That's fine. Then we solved two problems where the power emitted by a source was given. Based on that, we calculated intensity. Okay, so we visualized how the energy is spreading out. If it's a point source, energy spreads radially outwards. If it's a linear source like this is also called radially outward only, but perpendicular to the wire. Okay, not in all directions. Okay, only in directions perpendicular to the wire it will spread. Okay, wire or the linear source. And based on that, we visualized the surface and we calculated the intensity. Okay. The only thing left in this chapter is momentum carried by an electromagnetic wave and something called radiation pressure. Okay. Those two things we'll discuss in the next class. Okay, thank you all. We'll continue. Saturday, I may not be taking a class. Maybe tomorrow itself, some 15-20 minutes, we can finish off momentum and radiation pressure. I'll inform. Okay. Right. Thank you all.
Thank
Thank
you,
you,
sir.
sir.